So now from here on, the objective is going to be to actually understand how to use specific formulas for each type of differentiation, each type of functions to differentiate them or to find out the slope formula. So now let's say if I've got just like, quick idea from here, let's say f of x, if it is x to the power n, um, and we can obviously prove that the derivative of this, you would have noticed by now, is nx to the power n minus 1, but that's on observation. But it'll be interesting to actually show this formula using the first principle. So I'm just quickly showing this formula using first principle, though it's not needed, but it might be interesting to do for paper 3 for higher level. So what we can do is f of x plus h minus f of x. I'm not writing the limits and all here, just I'm writing the expression so that I can quickly finish it. So it'll be x plus h to the power n minus x to the power n over h. Obviously, let's say here, I'm just writing limit h tends to 0 once. Now, after this, what we have is if you open this up, it'll be x to the power n plus nc1 x to the power n minus 1 h plus nc2 x to the power n minus 2 h square and so on, and plus up till h to the power n and minus x to the power n over h. And of course, the limit is h tends to 0. Now, x to the power n and x to the power n get cancelled. You can clearly see that. nc1, as we know, is n itself. And that's the only part actually we need to be worried about. Because when I take h common, that's the only part which is without h. So it'll be nc1 is n, x to the power n minus 1, plus after that nc2, x to the power n minus 2, h, up till h to the power n minus 1, because if I remove one of the h, it will be left here. This h and h get cancelled. Rest of the term contain h, so they all become 0. The only term that doesn't contain h is this one. So the derivative of x to the power n, you can see how I proved this, nx to the power n minus 1. Also, this would have been quite evident from your previous results, like, for example, when we did the derivative of the first one. Now, when I did the differentiation of x squared, you would have noticed that the derivative of x squared for that part you got is 2x. So actually, if I did just now, a previous example, we did the derivative of x cubed, you would have noticed that part for that part, derivative was 3x squared. So same way, if I go on the iterative method, the derivative of x to the power n you'll get is n x to the power n minus 1. So this you can take as a formula given in your data booklet as well. So nothing to mug up about, but need to know how to apply this. So now, for example, let's say I have to differentiate y equals to, my function is y equals to x to the power 10. And I want to find the derivative for this. And obviously, using first principle will be very lengthy for this. So what we do is we just simply do dy by dx. Here, if I compare with x to the power n value is nothing but 10. So it's going to be 10 x to the power 9. So this is the simple, straightforward formula for differentiation. Now this is one of the easier sides. Let's just see how do we do the tougher questions based on this formula. So our first formula that is in use is currently the derivative of x to the power n is n x to the power n minus 1. That's the derivative formula. So now let's say when I have to differentiate now a couple of expression like here, if I have f of x is, let's say, which is g of x plus h of x. Now, if I have like two different sums, and then let's say I'm just making a constant here, let's say constant here, and then I'm adding another constant d here. So if I differentiate this, f dash x will be actually the derivative of the first function, g dash x, plus c is a constant. So that constant you don't touch. If a constant is with a function, you don't touch that. So that will be c times h dash x. And if a constant is alone, because if you have a horizontal line, its slope is always 0. So if a constant is alone, you make its derivative 0. But if a constant is with the function, don't touch it. Now, it might not be very clear here, but let's take an example what I mean to say. So let's say my function is x squared plus 4x cubed minus, or let's say plus 3. Now this is the function I want to find the derivative for. So at that stage, when I find out the derivative, f dash x is going to be 2x, because x squared is x to the power n. When you look at it, it'll be 2 x to the power 1 actually, which is n minus 1, and plus 4 as it is. Now don't touch this 4. That's the meaning of this when I said, because the function or with the variable, then the derivative is not 0 for that. In this case, you just find out the derivative of x cubed, which is 3x squared, and plus derivative of 3, which is 0. So what we get is 2x plus 12x squared as my final derivative expression for this function. Similarly, if we get like something which is like fractional indices, now let's say if we get something like here, f of x is x plus root x the whole square over x cube or something. And I want to find out the derivative for this. Now, lots of times what happens is the students differentiate numerator separately, differentiate denominator separately, and just divide them. That's not how it works. We have some rules and regulations for it. Obviously, there might be alternate methods, but since we haven't done any of the bigger methods, let us just first learn the basic way to how to do this problem. So first thing, what you can do is best way is to get each term in x to the power n format. And it cannot be in 1 over x to the power n format. And you can say, oh, I will differentiate denominator and keep 1 in the numerator as it is. So no. So what we need to do is make sure that your expression is only in the form x to the power n. So in this case, what we do is first expand it. So we'll be using the formula x squared plus 2 x to the power, it become 1.5 and plus x, because x times root x, as we can see, x times root x when we do will become x to the power 1.5, which is 1.5 over x cubed. Now, after this, you isolate each term. So it'll be x squared over x cubed plus 2x to the power 1.5 over x cubed plus x over x cubed. Now this becomes 1 over x plus 2x to the power negative 1.5. It become, because 1.5 minus 3 power, if you subtract, it becomes negative 1.5 plus x to the power negative 2. Because one of the x get cancelled and you take it up, it becomes this. Same way is for the first one, which can be written as x to the power of negative 1. Now, when I find out the derivative for this function, if you have, this is y, so dy by dx is going to be negative 1 x to the power negative 2 plus 2 times negative 1.5 x to the power negative 2.5 and plus negative 2 x to the power negative 3. So this is the derivative expression. And what I did is I'm applying the formula once I get it. So here you can see n is minus 1. So minus 1 x to the power minus 1 become minus 2. Same way. Here n is minus 1.5. So 2 times minus 1.5 x to the power, again minus 1.5 minus 1 is minus 2.5. Then x to the power negative 2 can be written as negative 2 x to the power negative 3. So this expression obviously you can simplify with the positive indices and all, but is the derivative of this particular expression. So you should know how to firstly reduce the terms, expand them, and bring it to the standard form in order to find out the derivative for that. So this is what I meant to do. Now let's just try to see which are the other kind of questions that can be assessed on this. So let's say f of x has been given to us as ax plus b over x squared. And it has been given to us as that f of 1 is, let's say, 0, and f dash 1 is 5. And you have to find out f of 4. So that's the question which we have, and let's try doing this. So in this question, what we have is f of 1 has been given to us as 0, which means that if I replace x with 1, so a plus b is 0. And f dash 1 is 5. So firstly, f of x is ax plus b x to the power negative 2. So f dash x will be a and plus b times negative 2 x to the power negative 3. So a minus 2b over x cubed equals to, this is the derivative. And now what I do is plug x as 1 and y as 5. So f dash 1 is actually 5. So it'll be a minus 2b equals to 5. So now what we get is we get two equations. A plus b is 0 and a minus 2b is 5. So if I subtract them, what we get is we get 3b equals to negative 5. So that gives me b is negative 5 over 3. And a will be 5 over 3. So my correct expression that you get here is f of x will be 5 over 3x minus 5 over 3x squared. So if you plug x as 4 now, here you get the value of f of 4. Now, so let's just progress towards the other types of functions, like, for example, the trig functions, exponential functions, inverse trig functions. So we'll have the set of formulas written in the beginning itself. And along with that, we'll be writing two other formulas that I call as product rule and chain rule. I mean, product rule and quotient rule. So first thing is that, let's say if I have a function, which is, I'm writing in this X list, and the derivative is f dash x. So now if my function is sine x, using first principle, we can show that the derivative of sine x is cos x. Now, if the function is cos x, the derivative of that is negative sine x. And all these formulas are in data booklet. If you have a ln x function, the derivative of that is 1 over x. While if we have log x function, log x to the base a, the derivative is 1 over x, ln a in the denominator. You got to remember, this is a very interesting formula because lots of times students just write the derivative of log x to the base a is also 1 upon x. So that you have to be very careful. So e raised to x derivative is e to the power x, while a to the power x, if you have any exponential function, a to the power x derivative is going to be a to the power x ln a. Now, these are the formulas which are mixture of HL and SL both. So please make sure to it that you remember. So these are the standard level common formulas. And these are explicitly the HL formulas. E to the power x is also in standard level. So now coming back to the next ones, which is like like for example, tan inverse and all. So first one is derivative of sec x. I mean, sec x formula is derivative of sec x is sec x times tan x. Derivative of tan x that you have is something called as sec squared x. These formulas are all are in your data booklet, so nothing to worry about. But yes, sometimes when you have better knowledge base, you will be able to prove all these also at the same time. So tan x is sec squared x. Similarly, cot x formula is a negative cosec squared x. And while formula for cosec x is negative cosec x cot x. And a few of the last formulas that we have, I would be writing is that we have tan inverse formula. The tan inverse x derivative is 1 over 1 plus x squared. Then you have sine inverse formula. Sine inverse derivative is 1 over root of 1 minus x squared. And cos inverse x formula is negative 1 over root 1 minus x squared. I have shared the data booklet with each one of you, and you can notice that all these formulas are there. So the only thing is that we should know how to apply these. Now, these individual functions might not be assessed like directly. Now, nobody's going to say, okay, find out the derivative of ln x function. So what is important is that sometimes we are learning some of the advanced techniques of differentiation apart from first principle. And the first rule that helps us a lot is the product rule. So product rule. Now, what exactly is product rule? Now, when you look at the situation where you can be thrown into is, okay, suppose if I have y equals to x times sine x. Now, there is no direct formula. I have the formula for x to the power 1. I have formula for sine x. But there is no direct formula for x times sine x. So in this case, how do we differentiate? What will be our skill of differentiation? And it's like, in this case, as you can see that when you have two functions, let's say one of the function is u of x, other function is v of x, if they're multiplied together. So when you do the analysis or the error analysis, to be frank, in this case, what you'll notice is that the dy by dx formula that comes is u v dash plus vu dash. Now, what does it dash mean? So u is like keep the first function as it is, differentiate the second, plus differentiate the second, keep the first one as it is. I mean other way around. So uv dash plus vu dash. So now, for example, x sine x, I can choose any one of them as u, other one as v. So let's say if I take u as x and v as sine x. So u dash and this is v dash. So u dash will be, derivative of x will be 1, because if I have x to the power 1, I can write on 1, x to the power 1 minus 1, which is 1 times x to the power 0, which is nothing but 1. And if I talk about v dash, is sine x derivatives cos x. So the derivative sine x is cos x. So now if I look at, I just use the cross multiplication logic, uv dash plus vu dash. So it'll be x times cos x plus 1 times sine x, which is dy by dx equals to. So dy by dx is x cos x plus sine x for this particular function. Now similarly, let's take one more example. If I have got x squared tan x, y equals to x squared tan x. Now, when I want to differentiate this function, it'll be dy by dx will be uv dash. So you should write down, in the beginning, you should write down, if you're not confident, u is this, v is, let's say, tan x, and vice versa. You can write down any one of them as u and other as v. There is no restriction for product rule. So u dash that you'll get is 2x, and v dash you'll get is a 1 over, v dash is x squared x, you can write down, um, uh, or you can write down 1 over cos squared x. So that's the thing. Now, answer for here will be x squared. Derivative of tan x is nothing but sec squared x plus tan x as it is times derivative x squared, which is 2x. So this is the product rule for when you have two functions. This is in your syllabus. But sometimes they also give you product rule of three functions together. So like, let's say I have got, instead of x sine x, I have got, let's say, y equals to x sine x times cos x. So how do we differentiate in this case? So we need product of three functions, not in your syllabus, just as additional entity I'm telling you. Now, when you have three functions, let's say if I have y equals to u, v, w, or even for matter of four functions, just apply the logic that I'm telling. Is you can see that you'll keep one function differentiated at a time and other two as the same one. So dy by dx in this case will be u dash vw uv dash w plus uv w dash. So these three functions are basically these three. The product can be differentiated as here. So u dash vw, uv dash w, and so on. So now, for example, if I want to differentiate this one, it'll be u dash is x, so its derivative is 1. So it'll be sine x times cos x plus uv dash w. So it'll be x as it is. V dash derivative sine x will be, you can see, is cos x. So cos x times cos x will become cos squared x. Similarly, uvw dash plus, so it will be x sine x times negative sine x, because cos x derivative is negative sine x. So if you simplify this, that's the answer that we get. So this is about the product rule. So our next part for this kind of rule is, the next half is also called as quotient rule. Now in quotient rule, actually what we have is, we look at, let's say, if you have a function which is in the form of u over v, so you have a function in numerator over denominator, like in form of fraction. Like, let's say if I've been given x over sine x, or for that matter, if I've got like ln x over x or something like that, or sine x over cos x, which is also the tan x. So tan x, if I want to find the derivatives of these functions, how do we do that? So when you have quotient rule, now you have, again, the formulas are all given in data booklet. These formulas, product rule, quotient rule that we're talking, all are there in data booklet. Now here, when you look at the dy by dx that you have got will be v squared, that's your v squared, vu dash minus uv dash. Now here you have to be very careful that numerator you take as u and denominator you take as v. There is no like flipping of the values. If you flip them, your answer is going to be wrong. So now how do we take this? So first you square the denominator and keep it as it is. Differentiate numerator minus, keep numerator as it is, differentiate denominator. So for example, if I'm differentiating x over sine x, so u is x, this is u, and v is sine x. So my derivative here will become dy by dx is going to become v squared, that is sine squared x, and sine x as it is, times derivative x, which is u, which is 1, minus x as it is, times derivative of sine x, which is cos x. So the answer is sine x minus x cos x over sine squared x. So this is the quotient rule by which you differentiate it. Now let's do one more example. Let's say I have ln x over x. Now, for example, ln x over x, how do we differentiate that? So y equals to ln x over x. When I do, it is going to be, first apply v squared. So this is going to give us dy by dx as v squared in denominator, which is x squared, x as it is. So you can see v as it is, times derivative of numerator, which is ln x, which is 1 over x, minus derivative of denominator, which is 1 times ln x. So when you simplify this, you get is 1 minus ln x over x squared. So this is your simple quotient rule. Now let us prove that how we get the derivative of tan x as x squared x. It'll be interesting to see how is it coming. So let us once again apply quotient rule for tan x and see what do we get. So when you look at tan x, so tan x numerator is sine x over cos x. I mean sine x over cos x is the expression here. Numerator is sine x and denominator is cos x. So this is u and this is v. So my denominator become cos squared x. And then what happened is that cos x as it is, derivative of sine x is cos x minus derivative of sine x as it is. Sine x is as it is now, and derivative of cos x is negative sine x. So what you see is the numerator actually becomes sine squared x plus cos squared x over cos squared x. So that's nothing but 1 over cos squared x. That is nothing but sec squared x. So you can see that how we can prove the derivative of tan x being sec squared x using quotient rule. So this fragment that we have is the backbone of entire differential calculus, and that's referred as chain rule. Now, when you talk about the chain rule, chain rule actually is just another technique to differentiate composite functions. Now, we got a way how to differentiate if you have product of 2 functions or 3 functions or 4 functions. We got a way how to differentiate when you have a fraction, but we don't have a way that how we can differentiate any type of composite function. So now chain rule is something that I would try to explain in my personal way, but there are definitely certain standard formulas that you need to know, and we'll try to touch base upon in next 20 minutes. So what exactly chain rule? Now let us say if I have given you is, okay, let's say differentiate x to the power 20. It becomes much more comfortable. Okay, so f of x is x to the power 20. So the derivative of this is going to be 20 x to the power 19. But now if I ask you a simple question is, okay, can you differentiate, let's say if my f of x is, instead of, let's say I'll take g of x, this is preferred to be g of x, it'll be, let's say, x squared plus 5x to the power 3 plus 20x to the power 9 to the power 20. Now, this becomes one of the biggest challenges for us is that, okay, how much expansion do we do? Like, do we write 60 terms of this, 55 terms, 20 terms? How many terms are right? It'll just waste our time. So in such cases, we have something called a chain rule. Now, chain rule is specifically for composite function, where we need to understand that, okay, if a given function is, let's say, of the form, let's say, f of x is something called as h of g of x. It's a composite function. If it is composite function, now what we do is actually, first step is to differentiate the outer function, which is the parent function, which is h dash of g of x. So I didn't touch internal function. I just differentiated the parent function, which is outside, times the derivative of the child function, which is inside. So the first you differentiate the outer one, and then you differentiate the product of the inner one. Now, how does it link to my previous problem, this example? Now, if you see here, if I say let's say my f of x is x to the power 20, h of x is x to the power 20, and g of x is x squared plus 5x cubed plus 20x to the power 9. I have found out h of g of x, which you can see up here. This is h of g of x. Now, if I apply this logic, it will be, okay, h dash x will be, it'll be 20 x to the power 19. And obviously I have to do h dash of g of x. It'll be, final answer will be, when I differentiate g dash x, will be nothing but h dash of, let's say, let's say in this question I have taken different notations. So let's say this is my f of x. So f of x derivative will be uh, the 20 x squared plus 5x cubed plus 20x to the power 9 to the power of 19 times the derivative of g of x, which is g dash x here, which is going to be 2x plus 15x squared plus 20 times 9, which is 180 x to the power 8. So that's the derivative of this. Now, whether you want to take in this way or you want to take in a formula way that I'm explaining next, is in case if you have been given, instead of x to the power n. Now, I'm just going to go a little bit towards the formula link. Instead of x to the power n, if we have been given, let's say instead of this, here I haven't written, so I'll just rewrite this. Instead of x to the power n, if I have been given some function to the power n. Instead of sine x, if I have been given sine of some function, which is like it's like a composite function where sine x is the parent function, and f of x that you see inside is the child function. If we have cos, instead of cos x, if I've been given cos f of x, instead of e to the power x, if I have been given e to the power fx, instead of ln x, if I have been given some ln of some function. How do we differentiate these? Is there a way that we can link up in much easier way rather than doing f of g of x and g of f of x, all this stuff? So what is the logic is, in this kind of case, I can explain you this in the simplest possible way that I'm trying to explain, is that you differentiate the function as you do normal function, like you do the normal parent function derivative. So first step is n times f of x. Don't think that you have been given some function. Here, derivative sine, you know, it's cos of function. Here, cos derivative will be negative sine of the function. So don't touch the child function in the first step. The e to the power fx is e to the power fx, as we know. ln fx is 1 upon fx. Since ln x is 1 upon x, I'm just writing here the derivatives of parent function so that you don't get confused. So these are the parent function derivative. Now, what's something that is missing out here is that you have to multiply with the derivative child function, which is f dash x everywhere. You just have to remember this technique that helps us do the things much faster than what actually we would have done using the f of g of x logic. Now let's just take the same example, like similar example. Let's say x squared plus 3x plus 5 to the power of, let's say, I'm just doing, let's say, this derivative. 1 over x squared plus 3x plus 5. So now you can either go with quotient rule, which is like not practically, I would not advise because you don't have like a function in the numerator, but still you can do taking function in the numerator as 1. But what is the easier way is to look at like this. X squared plus, I can just modify this function as x squared plus 3x plus 5 to the power negative 1. X squared plus 3x plus 5 to the power negative 1. And now you do the derivative. So when I look at dy by dx, it is going to be negative 1 x squared plus 3x plus 5. So my step number 1, you can see is I'm differentiating, ignoring the fact that, okay, it's like your x squared plus 3x plus 5 is also existing. So I'm differentiating as if I'm differentiating x to the power negative 1 function. So indirectly, we did h, the previous example, if you link, we did h dash x, like the outer one we have differentiated. Now inside one we have to do. So now into the derivative of this, which is 2x plus 3. And if you simplify this, it is negative 2x plus 3 over x squared plus 3x plus 5, the whole square. So that's your derivative out here. Let us take one more example. Let's take, for example, if I have to differentiate sine cube x. Now sine cube x, I don't have a formula directly. So lots of students, they just do is, okay, 3 sine squared x and done. This is wrong. This is wrong. Okay, so what we do is, this is sine cube x is not pure power function. It's a composite function. The sine cube x, if I have to differentiate, one of the very important type of question, because this kind of question students make a lot of mistakes. So sine x to the power 3 first we write down. So once we can see clearly that's like parent function is x cubed here. So differentiate as if you're differentiating normal function. Like suppose this is y. So my dy by dx is going to be 3 times sine x to the power 2, which is like 3 sine square x. But what was missing is you didn't multiply with the derivative child function. So it is like, okay, into sine x derivative is cos x. So this is the actual derivative of this function, this expression. So this is where you can see the power function being used to differentiate its derivatives of composite functions. So next up is let's take the chain rule of a trig function. Now, for example, if I have to differentiate cos of sine x, or let's say sine of some other function, sine of ln x or something. And now let's take one more example on exponential function. Let's say e of e to the power sine x. Now let's take another function is ln function, which is x squared plus 4x plus 3. So in all these cases, what I'm going to follow is like first step is that we differentiate the parent function and don't give any preference to the child function. So it'll be negative sine of sine x into, don't forget the derivative child function, which is cos x. Similarly, if I have sine of ln x, parent function is sine, so differentiate first. So it'll be cos of ln x times derivative of ln x, which is 1 upon x. Now, e to the power sine x. So e to the power x is my parent function. So differentiate it as it is. Ignore sine x. So e to the power sine x times derivative of sine x is cos x. Now, ln x is 1 upon x, you can see, or 1 upon fx here. So it'll be 1 upon child function as it is into the derivative child function, which is 2x plus 4. So these are some of the techniques that can be very, very helpful when you're doing the derivatives of different kinds of functions. So now what we will do is let us take some questions that are out of box, and you can see that there are multiple times of chain rules might be required. So let's take a couple of examples. The first one, what I can give is, what I remember is, let's say y equals to ln of ln x. Now this is a function where you're like, it's like grandparent here. So grandparent, then father, then child. So first differentiate grandparent, then come to the father, then come to the child. And all derivatives will multiply. So let's take first differentiate the father, grandparent. Here ln fx derivative will be 1 upon fx. So this, for grandparent, this will be still a child. Entire thing will be a child. So it'll be 1 upon ln of ln x times the derivative of, now ln of ln x. Now come to the father now. So now you're differentiating this, okay? So now for this, still it is not the child function. So you'll differentiate 1 upon the child function times the derivative child function, which is 1 over x. So you can see that here you have to apply the derivative chain rule twice. So now let's take an example where like you have a trig function, or let's say if you have cos of, let's say, sine of tan x. So in such case, what we have is cos is the grandparent. So first differentiate that. So it'll be negative sine of sine tan x. So first step, we didn't do anything to the father and child function. Now go to the father function, which is sine x. So it'll be cos of tan x. Now then you go to child function, it'll be sec squared x. So all these things, if you remember in a way that I thought, I think they make a better connection with the chain rule.